Welcome to today's Leapfrog Geothermal best practice. The theme of this video is building a temperature model from well data. My name is Bastien Poux. I am the Technical Sales Advisor for Energy at Sequent. It is my pleasure to present you this video. Please note, the objective of this video is to focus on the tools in Leapfrog Geothermal and to give you helpful workflow ideas and tips and tricks to elevate your modeling skills. The material covered in this video is meant to be high level and is using a simplified dataset. To build models from numeric values, such as temperature data in Leapfrog Geothermal, we use the Numeric Models folder located in the project tree. This tool can be used to interpolate numeric and upscaled well data, but also point data. It can be used for a variety of datasets, for example for pressure data, chemical species concentration, geophysical logs, and more. In this video, we will use it to build a temperature model from well data. To build the numeric models, Leapfrog Geothermal uses the fast radial basis function, or fast RBF, algorithm, which employs interpolation functions to estimate values from known data. This process is fast and dynamic thanks to this algorithm. You can then easily adjust the parameters of the interpolant to get a model that best fits your interpretation. The temperature data can be imported in the wells folder as a point table or a LAS file. During this video, a series of tips and tricks will be presented to help you understand the key concepts of the numeric interpolation and also to use some of the other tools available in Leapfrog Geothermal to adjust your model. First, we will see what are the different types of interpolant available in Leapfrog Geothermal and also the different parameters that can be changed to modify the results of the interpolation. We will then look at how to make some manual adjustments to influence the interpolation in areas away from the existing data. Finally, we will see how to use the newly constructed model to evaluate the temperature distribution on another object in your project, for example a fault or a plant well. We are now in Leapfrog Geothermal where we have created a new project. As a reminder, you have on the left the project tree, in the middle the 3D scene. Below the 3D scene is the shape list. At the bottom right you will find the property panel, and above the 3D scene is the toolbar. We will start by importing our topography. In the project tree, you right-click on Topographies, New Topography, Import Elevation Grid, and you can look for your DTM and open it. The surface resolution is 100. We can just import it and leave it named as Topography. It will appear in the project tree under the Topographies folder, and you can drag it into the 3D scene. The next thing we're going to do is import the well data. We right-click on the well data, import wells, and we're going to start by looking for the location file. It will automatically find the survey file because it was named survey, but you also have to add a new interval table. In this case is the casing diameter table. We are now going to import our well data. In the location table, the well ID, X, Y, Z, and maximum depth have already been selected, so we can click on next. In the survey table, we also have the well ID, the depth, dip, and azimuth. Here we also have the inclination, which is 90 minus the dip. It is not necessary to import them both. In the third table, we have also our well ID, our from-to for the intervals, the casing type, which we're going to define as a category, and the casing diameter, which we'll define as numeric. And you click Finish to import the wells. Even though we are not going to use the casing information to build our temperature model, we need to at least import one table made of interval in Leapfrog to be able to visualize the wells. Once it's imported, you can slide in the well traces simply to look at the wells under the topography. What we'll need to do now is import the temperature data. We right-click on the wells and we're going to import from File, Point Values. You could also import a LAS data if that's the format you have. And we can look for the temperature CSV file and open it. The first column contains the well ID, the second the depth, and finally the temperature. We are going to import the temperature as a numeric value. It is important to import those data in the right format to be able to build a numeric model. You can now click Finish to import the temperature data. They will appear in the project tree under your wells, and you can drag them into the scene. To visualize them better along the well traces, we're going to visualize the point as sphere by clicking on the pink button in the shape list. We can visualize here the temperature data along the well traces. Let's now have a look at the rules of numeric interpolation. Let's start with the basics of interpolant functions. The purpose of the interpolant in Leapfrog Geothermal is to describe how numerical quantity varies in the three-dimensional space. The interpolation produces an estimate, or interpolated value, of a quantity that is not known at the point of interest, but is known at other points. The estimates for unknown points, when varying the distance from known points, is controlled by the interpolant function. Any interpolation function and the various parameters that can be set for each will produce a model that fits all the known values, but they will produce different estimates for the unknown points. It is important to select the interpolation function and parameters that make the most geological sense. Leapfrog Geothermal uses two main interpolant functions, the linear interpolant and the spheroidal interpolant. On the graphs on the right, you can see the behavior in attributing an interpolant value based on the distance. Note that the lower the interpolant value, the stronger its influence in the model. We are going to start with the linear interpolant function and its parameters. There are two main parameters to consider for a linear interpolant function. The first one is the drift. It represents the model for value distribution away from data. When it is set to linear, the interpolant will behave linearly away from data. When it is set to constant, the interpolant will go to the approximated declustered mean of the data, which correspond to the average value of all the available data. The second parameter is the nugget. It represents the local anomaly in values. Graphically, it is the value of the interpolant at a distance of 0 from the existing data. Increasing the nugget will place more emphasis on the average values of the surrounding samples. The base range and the total seal define the slope of the interpolant. The base range is the distance where the interpolant becomes the total seal. In the case of a linear interpolant, changing the base range or the total seal doesn't have any influence on the interpolation. These parameters are shown in Leapfrog for the sole purpose to switch easily between a linear and a spheroidal interpolant. The spheroidal interpolant behaves differently. The total seal is an important parameter that defines the upper limit of the interpolant after reaching the base range. The base range is shown by the vertical yellow line on the graph on the right. The interpolant value remains equal to the seal short after reaching the base range. At the base range, the value of the interpolant is 96% of the seal if no nugget is applied. The base range also influences the distance to the values considered, like in the linear interpolant. The spheroidal interpolant also has the linear and constant drift, but additionally it offers the option to choose to have no drift. In that case, the interpolant will pull down to 0 away from data. Similarly to the linear interpolant, the nugget represents the value of the interpolant at a distance of 0. The alpha determines the steepness of the interpolant to reach the seal. A higher alpha will place more emphasis on the average values of the surrounding samples. So which interpolant is the best to build the temperature model, and how to set the parameters to better represent the distribution of values in the subsurface? Here are some guidelines. The linear interpolant will give the best results for temperature models and is also the easiest to use for this purpose. The base range and the total seal will have no influence on the interpolation results. The drift should always be set to linear as the temperature increases with depth and cannot be defined by an average background value. The nugget should be kept to 0. You can also add a trend in the model if your interpretation considers a plane, like a fold direction or a particular unit, as we will see in a bit, to have influence on the distribution of the temperature. For other types of data, such as chemistry, geophysical data, porosity values, we recommend starting with the spheroidal interpolant and change the drift to constant or none, as their spatial distribution is not directly influenced by the depth. We are now back into Leapfrog Geothermal. To build a numeric model, you're going to right-click on Numeric Model inside the project tree and select New RBF Interpolant. A new window is going to open, and we're going to start by selecting the numeric values we're going to interpolate. Here we're going to select the temperature data. Secondly, we will choose the interpolant boundary. Right now, it is using the extent of the DEM model, but we're going to change the minimum depth to go to 3.5 kilometers. The resolution is going to be lowered to 100. We are also going to rename the model Temperature Model, and now we can click OK. Leapfrog is going to process the temperature data to create the RBF interpolant, and it is going to appear under your numeric models in the project tree. We see here the object temperature model. This model is defined by its boundary, a possible trend, the temperature values that were used based on the well data, the ISO surfaces, and the volume. If we look at the ISO surfaces, right now there is 3 of them, 110, 180, and 240. This value has been randomly assigned by the software, but we can change them. You double-click on the temperature model, and you go in the last tab called Outputs. In the box in the middle, you can change the ISO values. Here we see that the values go from 0 to 307. We're going to set one at 50, one at 100, 150, 200, 250, and 300. You can add more values by clicking on the plus. And then you can click OK. And the software is going to reprocess to create ISO surfaces for each of these values. Once processed, they will appear under the ISO surfaces folder. We can drag them in, and now we can observe the different ISO surfaces in our 3D scene. As you can see here, there is a strange behavior outside of the data, so we are going to have to change the parameters of the interpolant. Double-click on the temperature model and go into the Interpolant tab. As you remember, we recommend using a linear interpolant. The cylinder range don't really matter. The nugget is set to 0, but the drift was set to constant. We are going to change it into a linear drift and click OK. Leapfrog is going to reprocess the model, and we can now see the results with a linear drift. We can see that the interpolant has a linear behavior away from the data, which gives these sub-parallel surfaces. If we cut the model in the middle, using the slicer in the toolbar, we're going to see the behavior of the interpolant where we have the data. We see the wells here in the middle, and by pressing Ctrl, right-click of my mouse and moving the mouse, I can move into the model. For the next tips and tricks, we're going to see how to manually edit the model by integrating some temperature data at the bottom of the model. For this, in the project tree, you can right-click on temperature model values and add a new contour polyline. The value you will define here is the temperature of the lines you're going to draw. To complete the surface at the bottom of the model, we're going to draw a line at 300 degrees. The name of the contour line will automatically update to 300. We can now click on OK. And we will now start to draw directly in the 3D scene. The tools are available in the toolbar above the 3D scene, and we can select the pencil, and we make sure that we are going to draw on the slicer. Our line will be drawn at about minus 3000 meters to match with the deepest observation of a 300 degrees in one of the wells, and we draw a polyline on both sides of the data. Once we save, the software is going to reprocess the model, and we're going to see our new contour polylines being used to build the 300 degrees ISO surface. But it also will have an influence on the other ISO surfaces for the other values. As you can see while we are moving inside the model, we can see that the RBF function is using both the well data and the contour polyline that we draw. You can at any time go back to your 300 degrees ISO surface with the polyline. You can modify them or add new ones. Next, we will compare our model using a linear interpolant with the same model if we were using a spheroidal interpolant. We're going to right-click on the temperature model and make a copy of it. Change the name to spheroidal and click OK. We're going to double-click on this new model and go to the Interpolant tab. The interpolant is going to be changed from linear to spheroidal. You can see the graph below has been changed. And now we click OK. And Leapfrog will reprocess the model. To see the difference, we will look at one of the surfaces in each of the model. We're going to use the ISO surface for 250 degrees for both the linear and the spheroidal interpolant. We can see that they are quite similar, but their behavior away from the data is a bit different. And this is directly related to the range of the spheroidal interpolant. If we go into the parameters in the Interpolant tab, we can see that the range is 4,000 meters, which represents a pretty large range, and probably covers most of the well data. We're going to put a lower number, like 1,000 meters, and click OK. The surface is being reprocessed, and the result shows these high and low temperature spikes, which doesn't represent the reality of a temperature distribution. If you drag in the temperature data into the scene, you realize that there is little correlation that's being made by the interpolant between different wells. So now we will see if we change the interpolant and assign it a range that is longer than the distance between the wells. By putting a very high value, I can see what is the maximum base range, 40,000. The wells are less than 10 kilometers apart. We can use the ruler available in the toolbar to measure the distance between the two wells that are the further away. And we can see there's about 7,000 meters between those two wells. In the first 7,000 meters of the spheroidal interpolant, you can see that the relation between the distance and the interpolant is linear. The interpolant only starts to behave differently when we reach about 14,000 or 15,000 meters. We can now click OK to reprocess the surface, and what we will see is that the surface of the spheroidal interpolant is very close to the one of the linear interpolant. The last thing that we can integrate into a temperature model is a trend. For that, you need to have a plane direction, corresponding, for example, to a fault. Here, I don't have a geological model with faults, so I'm just going to import a mesh corresponding to a fault surface. If I drag it into the scene, I can see my fault in the middle of my temperature model. The first thing I would have to do is to create a plane that has the same direction as my fault. For that, I'm going to do a slice in the middle of the model. I'm going to go on the side of my model and use the tool in the toolbar to draw a new plane. And I'm going to do a plane that matches my fault surface. We can see it in transparency gray here. We can stretch it by putting the red arrows on the corner. And this is the plane we're going to use to apply a trend. To apply a trend, I can go in my temperature model properties and go into the trend tab. Here I can simply set from plane, and this is going to copy the dip, azimuth, and pitch corresponding to the plane I draw. The ellipsoid ratio by default is 331, which I'm going to leave like this for now. And now we can click OK. The model is being reprocessed, and we can already see the 250 degrees isosurface. And we can see how the model has been stretched along the plane direction, which corresponds more or less to a north-south direction. To remove this trend, double-click on the temperature model and go in the Trend tab. Click on Set To and choose Isotropic. This will remove the plane from the trend, and the model is being reprocessed without the trend. For the next tips and tricks, we will see how to evaluate the temperature model onto our surface. The idea is to project these different isosurfaces on the surfaces of the fault. To do this, you are going to right-click onto the surface and select Evaluations. A new window will open where you can select which model you want to evaluate on the surface. Click on the temperature model and the green arrow to put it in the selected models. Remove the isosurfaces from the 3D scene, and in the shape list, select your fault surface, and in the first drop-down menu, select the temperature model. We now see the temperature distribution on the fault. To change the color distribution, select the second drop-down menu, where you can edit the color map and choose the curve points. Click Close when you are done, and you can already see the new color distribution on the fault. You can do this kind of evaluation on different types of objects in Leapfrog Geothermal. In the second tips and tricks, we're going to see how to do it on a planned well. You can plan a new directional well, or you can simply import a directional drilling plan. Here I'm going to import my planned well, which is going to show me the drilling plan in the new window, and I can also see my planned well in the background. I can make the line solid by clicking on the pink button. And I want to evaluate my temperature model on my planned well. It is the same procedure as for the fault. We're going to right-click on the planned well, select Evaluations, and move my temperature model into the selected models. When I click OK, I can look for my planned well in my shape list, and in the first drop-down menu, I will select temperature. What we see now is the temperature distribution along the planned well. This workflow is particularly useful if you are planning a new well and want to make sure that you are reaching the maximum temperature possible at the bottom of the well. If you click on the drilling prognosis, you can see the numeric values of the evaluation. You can also select all the rows and copy them to use them in a spreadsheet and do other analysis. This is the end of this video on how to build a temperature model from well data. I hope that the tools presented and the techniques shown will be useful to you and your team for your future modeling projects. If you have any question, do not hesitate to contact us at support.energy@sequent.com. Thank you for watching this video.